Welcome. Today we're going to talk about equivalent expressions involving exponents and the different ways you can see a exponential equation that are all basically the same equation, just written in a different form. Let's start out with something very, very simple. Let's say we had 4 raised to the 12th power. How many different ways could we write 4 raised to the 12th power? Well, there are a lot of different ways we could write 4 raised to the 12th power. We could actually see it as 4 to the 3rd power in parentheses raised to the 4th power. There's nothing wrong with swapping the position of these two, do 4 to the 3rd power raised to the 4th power. Because remember, by our property of power rule of exponents, we multiply those two together. 3 times 4 is 12, no matter which way we do it. We could also see 4 to the 6th times 4 to the 6th. We could see it as 4 squared times 4 to the 10th, because by our addition rule, both of these are equivalent to 6 plus 6 is 12, 2 plus 10 is 12, right? Different ways we could represent the same exponential expression. We could represent it as 1 over 4 to the negative 12th if we start including negative exponents. Then we could actually do something like 4 to the 20th over 4 to the 8th, because then what happens when we minus 8 from 20? These are all equivalent expressions. They could even try to be trickier and do something like this: 2 squared raised to the 12th. What do we get when we square 2? That's our 4. It's just the 4 written in a different way. So again, all of these are equivalent expressions. We could actually do the 2 squared raised to the 3rd raised to the 4th. That's an equivalent expression. All of these are exactly the same as being 4 to the 12th, just written differently. Sometimes when we're given an exponential equation and we're asked to find a different representation, sometimes the easiest and best thing to maybe do is to break down the exponential equation into prime numbers. What I might mean by that is this. Let's say I gave you 6 to the 3rd power divided by 3 to the 3rd power. What we could do, rather than evaluating it, rather than trying to take a calculator and doing 6 to the 3rd and 3 to the 3rd and then simplifying, if we were just to try to simplify it using exponents, what I could do is realize that that 6 is a 2 times a 3 that we're raising to the 3rd exponent over this 3 to the 3rd. Well, now what I can do is I can raise each of those factors of 6 individually to a power of 3. So I can go 2 to the 3rd times 3 to the 3rd over 3 to the 3rd. And then we notice that we have something that's the same top and bottom in common. They can cancel, and we're left with just 2 to the 3rd. Now, some students would say, oh, well, I noticed that's just 6 divided by 3, which actually you can do as long as they have the exact same exponent. The same thing applies to multiplication. In other words, if I gave you 2 to the 5th power times 3 to the 5th power, we don't add the exponents. But as long as the exponents are the same, we could write that as a 2 times the 3 in parentheses raised to the 5th power, or in other words, 6th raised to the 5th power. So we can break numbers that have exponents on them into their individual factors raised to the same exponent. So let's show one more example, and hopefully this will be enough to get you through the assignment. But let's say someone gave you something like 5 to the 6th raised to the 4th. They might give you many different forms that this could be in. Most of the ones that you would recognize would be like 5 to the 24th, because normally we want to simplify it. But if they're just trying to make sure that you can see equivalent expressions, they might give you 5 to the 4th raised to the sixth. They might switch the positions. They might give you 1 over 5 to the sixth raised to the negative 4. And they might use a negative exponent, because if I plug in this negative 4 times a 6, that's negative 24, but that brings it back up. The negative brings it back to the numerator. They might try to even be very tricky, and they might show something like 10 to the 24th over 2 to the 24th. And it's probably easier to try to simplify what they give you to see if it equals this. In other words, always simplify this to its simplest form, 5 to the 24th, and then go through and do that with everything else. And if it simplifies to 5 to the 24th, then it's equivalent. So this, again, it looks a little bit confusing, but since 10 has a factor of 2 and they have the same exponent, I want to emphasize that they have to have the same exponent, then you can reduce it by that and write that as, and again, I'm going to write it like this: 5 to the 24th times 2 to the 24th over 2 to the 24th, because what I did was I broke that 5 into, or that 10, into its two factors of 5 and 2, both raised to the 24th, and then the 2 to the 24th cancel, and I'm left with 5 to the 24th. Because you might get something like this. You might get something like, 9 to the 5th over, let's do something like 6 to the 5th. And if you'll notice, 6 doesn't go into 9. You can't go 9 divided by 6. But what you could do is you could do a 3 to the 5th times a 3 to the 5th. That's my 9 broken into its two factors of 3, both raised to 5, the 5th exponent. I'm going to break the 6 into a 3 raised to the 5th times a 2 raised to the 5th, because that's the factors of 6, 3 and 2 raised to the same exponent. And now hopefully you see that they both have a factor of 3 raised to the 5th, and I'm left with 3 to the 5th over 2 to the 5th. And we could write that as a single fraction. We could say it's 3/2 in parentheses raised to the 5th. Or we could even write it as 3 to the 5th times 2 to the negative 5th, right? We could bring this up, making it a negative exponent. So this would be equivalent to that. These would be equivalent to that. So sometimes it really helps to break down those numbers into its prime factors, each factor being raised to that exponent. If you have questions, please bring them to class, and I will help you as much as I can.